Okay, so hello everyone, this is Akshay here, and today's question is about find the first and last occurrences of the X, right? So, to do this question, we have some approaches, but let us read the question. So, given a sorted array of n elements with the possibility to duplicate to find the indexes of first elements, the task is to find the first and last occurrence of X. So, similarly, in this case, 1, 3, 4 times 5, 67, 1, 2, 3, and 125. We need to find the first and last occurrence of the given x equals to 5. You can clearly see that the first occurrence is at this index, and what is this index 2? So that's what in the output. The last occurrence of the 5 is here. What's the index here? 5. So that's what present in the output, and similarly for the next cases as well. For x equals to 7, there is only one occurrence. So the first and last would be this particular index, that is 6 and 6. Correct? Okay. So if you remember, we have done the same type of question in day 296 on the name of number of occurrence. So let us see, first of all, let us go in the flashback that what was this question. Because once we have done the same question in past year, so you must be able to figure it out that if another question comes again, you must be able to figure it out how to solve it. So if you see this question, we have again given a sorted array of size and number x. You need to find the number of occurrences in the x in the array, right? So that means for x equals to 2, you need to return the count of the number of 2, which is 4 here. So what were the methods that we saw here? The first methods were that we saw using the linear search, right? That is storing the first occurrence, or we can just initialize a counter variable whenever we are getting array of I equals to x, just counter plus plus and return the counter. The second method we saw was using the map. And the third method what we saw was using the binary search. And how binary search was coming in play? That since it's a sorted array, so we run two time binary search. That is, first we find the first index, then we find the last index, and then we return the last index minus first index plus 1. That was this question. But in this case, in this given question, we do not have to do that. We just have to run binary search two times, that is for first and last, and we can just return that those indexes. As you can see, this is my GitHub code file for the particular day 296, and this would be the same code that will be running here again, right? Okay, so now for the viewers who have watched this 296 video, for you guys, I don't think this video is required. अगर आपको फिर से, if you are needing this video help, then definitely there is some lag, correct? Improve that particular thing, and it should not be happening in future again, correct? That would be beneficial for you. Now we are viewing it for the first time. Now let us see that how we can solve this particular question. So I'll explain each and everything again here in short, or let's say in very brief. So what would be the first approach to solve this question? Again, you have two approaches. You can first use a linear search, right? And in linear search, what would be the time complexity involved? O of n. And n is given is 10 power 6, which is less than 10 power n. And that is why a brute force. That is why a brute force will also get submitted for this particular question. Next, we'll be looking at the binary search, that will be finding the first and last index. And since it is log n, then log of 10 power 6 will be again less than 10 power 8. And that is why our optimal solution will also be submitted. Okay? Let us see first for the linear approach. So what we're going to do is linear approach is, let's say you have the array elements 1, 1, 4 times 2, and then 3. You will run a for loop. You will first initialize your first as -1 variable, and then let's say have a last as -1 as well. You will need a for loop that going from I equals to 0 to I less than n, I plus plus, right? Now whenever you encounter a particular element which is equals to x, what you need to check that if my first, if it is equals to -1, that is we have not initialized our first variable, right? So just once, because whenever you encounter the x variable first, you just need to store that index only once in your first. So that is why I'm checking. If it is not equals to -1, then store that particular I in your first. And what you will do, and you will store that particular I every time in the last variable for every time you will encounter the particular x, correct? तो इससे होगा क्या यार, for I equals to 0 what will happen? Nothing will happen. No updation. For I equals to 1, no updation. For I equals to 2, we encounter the 2, right? So what will happen? The first will be pointed to 2 and the last will also be pointed to. For I equals to 3, what will happen? First will point to again 2, because it will check if it is not equals to -1, right? तो यहाँ पे updation होगा ही नहीं. And L will be pointed to 3. Similarly for I equals to 4, L again will be pointed to, okay, I think you cannot see my screen. Okay, L again will be pointed to what? 4. For I equals to 5, L will be again pointed to 5. Let us name the indexes 0, 1, 2, 3, 4, 5, and 6. For I equals to 6, nothing will happen. And you will just return at the last. You will just make an array list because the return type is array list here of integer type. And you will just add first and last in your array list and you can return that particular list. Correct? Now please pause this video here. Try to code this approach both in Java and C++ and then we can resume. Okay, so that is the C++ code in Java. Let us hit the 7 button. We have already analyzed the time complexity is the O of n, and it's pointing to 10 power 6, which is less than 10 power 8. So this solution definitely gets submitted, even though it is a brute force method. Correct? Let us switch back to Java now. So that's the code in Java. Only changes we need to do that in vector in C++ and array list in Java, and that's it. Let us hit the compile button, and now let us hit the submit button. Wait for the results to pop up. Okay, great. So it's been successfully submitted now. Okay, so I have now commented our first approach, and without explaining the second approach, I will directly uh, tell you that this is the particular approach that we solved in day 296, and that's the reason here. Whenever you solve a code in the past, it must come handy. अगर आपने if you have saved in DSA repository, well and good. It should be else it should be in your mind, right, that how we have done in past. So what I will do first of all is that I will copy the exact code that is present in the here that we have done in the past, and then I will do some changes that how we can run this code, and then I will go with the explanation because I just want to show you that whatever we do in the past, whatever question we encounter in the past is very important here. That's the standard uh, basic questions, and you need to remember it. You need to keep on revising it, that once again if it comes in the future again, you'll be able to solve it. Correct? Okay, so that was the code for finding the which one, this was the last index was this is responsible for finding the last one. No, it's the lower index, right? So it is responsible for finding the first occurrence, and this H index is responsible for finding the last occurrence. So well and good, we are storing the calling the functions, but instead of doing this thing, we just need to do some things. We just need to copy this code from here and just paste it here, uncomment these lines, and see, we are good to go. So the only reason I emphasize on copy and pasting the code from our past, because I wanted to show you that you must remember what you have done in past. If not, if the question was very new to you when you solved it for the first time in day 296, let's say, then maintain a copy and keep on revising the standard algorithm, the standard question. Like the standard question must be in your mind so that if any variations come again like this one, you'd be able to solve it without looking at the code, without looking at the explanation again. Correct? Let us now hit the 7 button for this code as well, and then I will show you a dry run for this code or how this code was written. Great, yeah. So we have done this question, we are done here. But now let us resume with the explanation now. The two things you can do here is that you can go and watch this video number of occurrence where I have started explaining the third approach, right? But in very brief, I'll just show you that what are all the cases that how we need to handle. So let us write a very standard template of a binary search and then you can fill it. Okay, so first of all, we will define these two cases, how it is written. So we have a standard template. We need to just handle three cases. That is, if your array of mid, how we calculate the mid is nothing but low plus high by 2. If array of mid is greater than x, equals to x, and less than equals to x, right? So how we need to handle it. So first of all, let us fill these two standard cases, greater than x and less than x. So let's say you have an array element like this 1 2 3 4 5, and you need to find x equals to 2. Since it is sorted one, that is why we are doing a binary search, neglecting the left half and the right half. So how it works, we find the mid element. Mid is nothing but low plus high by 2, that is 4 plus 0 by 2, which will land you to this index 2. Now the element you need to search is 2, and the element where you are using this mid pointer is at 3, and what you need to search is lesser than this element. So can you say that I can neglect this particular right half because my element that is to be searched is already less than array of mid, right? So what I will say that first my low and high was pointing at this. I find this mid, I saw that my array of mid is greater than x, and I neglected the right half, and I will say my high is equals to mid minus 1. So high is equals to mid minus 1. So that's what I will write here. High equals to mid minus 1. Correct? Okay. Now imagine this case again. You have a low pointer here. You have a high pointer here. Now the element need to be searched is x equals to 4. You did low plus high by 2, in which you land you at this index m. which the indexes are 0, 1, 2, 3, and 4. Now you can clearly see that the current reference to the index which you are at index 2 and the element is 3. But you need to search for the element which is greater than this particular mid. So can I say that I can neglect my whole left half and I need to perform the binary search in the remaining right half? So what I will say, now my low would be this one, which is nothing but, if I represent in terms of mid, which would be nothing but low equals to mid plus 1. So that is what I'm writing here. Low is equals to mid plus 1. I just need to check that how we need to handle the case if it is equals to x. So now let us run for this particular case. So low and high would be here. Mid would be pointing to this side, right? Right now I'm finding, let's say, the last occurrence. We are writing the binary search code for the last occurrence. And I know that in my array of mid, like this, is equals to x, x was equals to 2. I need to find the last occurrence. What can I say? That I need to do the binary search again in the right hand side. Because if array of mid equals to x, then there is a probability that we need to move, that there will be more 2's in the right hand side, and that's what our use case. We need to find the last occurrence. So that is why I'll be doing the binary search in the right hand side. So I will say low is equal, the new low would be my this one, and my high remains same. So I will say my low would be nothing but mid plus 1. And while I'm moving in the right hand side, that I said there was a probability that you may find 2 in the right hand side, but there would be a probability that no 2's are present. And once you have landed at this mid index, that was the only 2 you have. So I'm talking about the case 1, 1, 2, 2, and then 3, 4, 5, like this. So low would be here, H would be here, mid would be here. Correct? There are no 2's there. So that means whenever you are moving in hope that you will get another 2 in the right hand side, first of all, you need to store that answer as well. So I will say that I will say my index is equals to mid. I will store that particular mid, and then I will move in the binary search in the right hand side. Correct? What will happen now? My new low and new high is like this, and my new mid will come like to this pointer. Right? Now what will happen again? I will store the mid. So first of all, mid was at this iteration, mid was equals to 3. Now at this iteration, mid is updated to 5. Right? Again, I will search in the right hand side direction. Let me change the color. So my new low and high would be pointing to this index, that is 6. I will calculate my new mid, that is again 6 plus 6 by 2, which will give you a 6 again. And now you can clearly see that your array of mid is pointing to which element? 3, which is greater than your current element to be searched. So definitely I will neglect all the right hand side elements and I will continue my binary search in the left half. Right? So your new low would be nothing but this particular mid minus 1, that is 5, and your high remains same as 6. Now you need to stop it here because the binary search has a condition. While low is less than equals to high, then only you need to perform the iterations. Yep. So what I said, the if the element is greater than x, you need to do high equals to mid minus 1, right? So high would be nothing but 5 and low remains the same, right? So low equals to 6 and high equals to 5. I need to stop while low less than equals to high. Definitely we will be stopping it here, and we will be returning the last most updated index for this mid one, for this IDX, right? So it would be 5. And at last we will just say return IDX, correct? After the while loop. Right? And that's what we have written in finding the last occurrence of our code, a higher index. You can see in the else if case, we are doing index equals to mid and low equals to mid plus 1. What are the changes we need to require if we do for finding the first index, finding first occurrence? Please pause this video here, try to code this thing, try to think what we need to do here, what the changes we need to do here, because these are the standard case. It will hold for both of the cases if you're finding the first or the last occurrences. Correct? Okay, so let us resume with the dry run now. So in the same dry run, let's say, or in the same dry run, let's say. So first of all, our mid was pointing it here now. And what we did, we stored the answer and we moved in the right hand side in hope that there will be more 2 present in the right. And since we find the last occurrence, so that is why we did the binary search in the right hand side. But what I need to do is, I need to find the first occurrence. So I will say the same thing, just the reverse of it, that the mid is here. Now there is a probability that there will be more 2 present in the left hand side, and I need to perform the binary search in the left hand side. So that means I will store my index again, that is true, But the another thing that you need to do is that you will completely neglect the right half, and you will say my low would be remain same and high would be here, right? So I will say nothing but high is equals to what? High is equals to nothing but mid minus 1, right? So high is equals to mid minus 1. So this is for finding the first occurrence, and this is the changes we need to do for the last occurrence, and that is it. That's it. Let us do a very quick dry run here. Let us do a very quick dry run here. So what were the elements? The elements were 1, 1, 4 times 2, and then you have 3, right? The indexes were 0, 1, 2, 3, 4, 5, and 6. Low is here, high is here, your mid is here. No, not here. Your mid is here. Now I need to neglect these half, and I need to perform binary search in the right in the left hand side. But first we have to store the answer for this thing. The mid is updated to 3. I'll perform the binary search in the left half. So low will be here, my high would be here. Now my new mid would be here, right? That now the element which I'm pointing at is 1. It itself is lesser than my which one, the element to be found. So I'll again neglect this half, right? And I will say my low would be mid plus 1. So no low, new low would be here, and new and the high remains same, so high is here. Now again mid would be calculated. So this is my second iteration, this is my third iteration. Mid would be calculated 2 plus 2 by 2, which will give you as 2. Now you can see that the area of mid is actually equals to a given x, correct? What we need to do is then we need to again store this particular 2. So we will store 2 here. First it was 3, then 2. Then again, if it is equals to x, then we need to again neglect the right half and move in the left half, right? So what I will do, that my high, low remains same, and high would be no, low remains same as 2, and high would be mid minus 1. So 2 minus 1 would be 1. That is, we are searching in the left half, but we can already see that we already searched in the left half, and that is why we are getting an inequality where low is greater than equals to high, right? We need to stop here. We need to return our last index, which was updated, that is 2. So we will get the first occurrence as 2 in this case. And when we did the dry run for finding the last occurrence, we have that as 5, right? We have that as 5, and that we need to do now. Just make an array list of the integer type and just show this answer, this first and last, and you will be good to go, correct? Okay, so that's what we have done here. The same code is for finding the higher index. I already explained you the case. This for the lower index, I already explained you. What else? We made first and last, we stored in the array list. Just add the first and last, and that's it. So we have already submitted this code. Let us see for the C++ now. So in C++ as well, everything remains same. Instead of using an array list, you will use a vector here. Instead of using dot add, you will use dot pushback. This high index, finding the higher index is same as we have done in Java and in the dry run. The lower index is same as we have done in Java and in the dry run. Let us hit the submit button now. And once again, I am emphasizing on this that you must not forget what you have done questions in the past. If you have remember, I have just copy pasted this code from this day 296, and we have done this question. So if I'm explaining you, although it was not for the explaining purpose, then I would have done this POTD challenge in, let's say, 2 to 3 minutes, right? So that's the impact you have when you remember your previously done questions, correct? Okay, now let us end this video in the good note, and do not skip the videos here. In the last video I saw that I made on the previous POTD. So I made a 20 to 22 minutes video because there were 4 approaches to explain, and I saw the views were very less. So I am again saying, if you are just following me for the solution, better do not do it. And if you are actually following for learning and understanding the problem, then you better watch the full video to have the full knowledge, right? Now let us end this video. Let us meet again in tomorrow's streak of day 390, 330. Till then, keep learning, keep growing. Bye bye, and take care, guys.